This video documents the design of a control board that uses the PIC16F18455T microcontroller. An effort has been made to document everything from concept to board creation and also the development of the firmware. The purpose of the controller board is to turn off the water pump for my hydroponic system. As you can probably tell from this video clip, this is my first attempt at growing leafy greens hydroponically. Being an electronics expert, everything that I build that has water in it leaks. When it leaks and I am not around, the pump would continue pumping even though the nutrient solution was going all over the floor. It would not stop pumping even though the reservoir was dry. I put plastic bag material over each end of the rain gutters so that the leaks would go back into the reservoir, but this only partially worked. The bags would not drain properly and made large filled areas like water balloons before dumping onto the floor all at once. Luckily, my garage came with a drainage system. Unfortunately, any small leak would empty the reservoir if I was not checking it all the time. There are two 12-volt submersible pumps. Each pump will require a separate PC board. Here is a picture of the two boards in operation. Each board has two red lights lit. One of the lights is for the reservoir and one is for the flow detector for the pump. Here are the specifications for the circuit. This describes the functions that the board needs to perform without going into much detail. It is just a broad overview to help with the development. I investigated a number of available types of sensors. The only sensor type that meets the circuit specifications of being cheap, reliable and easy to make is the capacitor or the float switch. Luckily, if a circuit is designed to use a capacitor for water detection, the same circuit can also be used with a mechanical switch. The cable was bought on eBay and I have not called the phone number on the tag. The Carroll part number is C074A. The cable contains two 24-gauge wires, a foil shield and a drain wire. I will connect the drain wire to ground on the driver end, and leave it unconnected at the sensor. I will be testing a length of 10 feet because this is the maximum length necessary for my hydroponic cabinet. I will use blue removable painter's tape. This will be folded over and stuck together so that the sticky side of the blue painter's tape is both on the top and on the bottom. The shipping tape is applied with the sticky side up. This layer of shipping tape is applied with the sticky side downwards. I will attach the driver end of the cable to a connector that will fit the adapter on my signal generator and also allow me to connect the scope probes. The signal generator will be set to 5 volts with a 2.5 volt offset, a 50% duty cycle and a frequency of 3 kHz. The lower blue trace of channel 2 is connected to the signal generator and to one of the plates on the sensor. The upper yellow trace of channel 1 is connected to the other plate of the sensor. The change in the amplitude of channel 1 can be seen to be proportional to the percent of the sensor that is below the surface of the water. I repeated the test at 6 kHz because, while 3 kHz would be okay to easily convert to DC, a higher frequency would make less ripple. If the frequency is too high, I would need to choose a more expensive operational amplifier. An amplifier is necessary because the input impedance of my scope is 100 kΩ, but the recommended input impedance of the PIC is 10 kΩ. There would be very little signal from the sensor plate if the load was 10 kΩ. This is a detailed description of the electronic design. I will begin with the driver for the sensor plates. It is desirable for one sensor to keep working even if all the others are shorted to ground, so each sensor plate is separated from the driver by a 2.2 kΩ resistor. According to the math, the driver will need to source 16 mA. While a digital output directly from the PIC microcontroller could supply this much current, it is better to use a more rugged device when connecting to things that are off the board. A first glance at the datasheet for the op-amp shows that the common mode range includes ground. When I made a breadboard of this circuit, it was unstable if the inputs were at ground. In fact, the output was a 60 Hz hum. The reason is that the output swing does not include ground. The reference voltage can be higher than one Schottky diode drop without affecting the operation of the board because of the peak hold circuit that I will talk about later. I decided to set the reference voltage at 2 Schottky diode drops so that there was some margin. These diodes were chosen because 8 of the same diodes are used in the peak hold circuit, and the same diode will work fine here. I added 2 capacitors to reduce the noise from the diodes. The 0.1 microfarad is for the higher frequency noise and the 1 microfarad capacitor is for the lower frequency noise. The sensor plate average voltage is set to the reference voltage through R3. R2 and C1 reduce the spike on the positive going edge of the received square wave. This is necessary for shorter cable lengths where the cable capacitance is not enough to dampen the spike. Without these components, the higher voltage spike would make it really difficult to deal with different cable lengths because the longer cable lengths have no spike due to their increased capacitance. R2 also helps isolate the op-amp from static electricity due to the user touching the pins. This is referred to as ESD or electrostatic discharge. The reference voltage is also connected to the gain setting resistors R6 and R7. The gain will not really be 3, as the values would indicate, because the values are not matched on the positive side of the op-amp. Averaging the wave shape for various cable lengths was more important than having a precisely linear gain. The capacitor C3 reduces the bandwidth to reduce the possibility of oscillation. C3 may not be necessary because the bandwidth of the LM2902 is not really great enough to worry, but it is there just in case. The peak hold circuit consists of a diode, a resistor, a capacitor and the input pin of the PIC microcontroller. When the output of the op-amp is 0.3 volts higher than the voltage at the input pin of the PIC, the diode will conduct and bring the voltage at the input pin of the PIC to 0.3 volts lower than the output of the op-amp. Since the actual input impedance of the input to the PIC is not known, the time constant and hence the decay curve of the voltage at the input pin cannot be calculated. I used the values for the resistor and capacitor to make a desirable time constant and checked it experimentally. The choice of 0.1 microfarads for the capacitor was influenced by the use of this same value for many of the bypass capacitors elsewhere on the board. For the following lab videos, the external trigger will be connected to the drive for the plates. Channel 1 will be connected to the output of the op-amp and channel 2 will be connected to the input pin of the PIC at D1 pin 1. Please be aware that the value of R2 was changed from 1K to 10K to more closely match shorter cables. If you were to need cables longer than 10 feet or so, this is the component that you would need to change. This is the result with a 1 foot long cable. Channel 1 is the yellow trace and channel 2 is the blue trace. This is the result with a 3 foot long cable. The reference for the analog to digital converter in the PIC is 4.096 volts, and this is the maximum voltage that can be measured. The maximum voltage is reached before the sensor is fully underwater. This is the result with a 10 foot long cable. The change is much less. While this amount of change is sufficient for sensing the presence of water, a larger plate size might be necessary for greater precision. A greater precision would be helpful if the circuit is being used to trigger on the moisture content of the soil. The programming port pins were chosen to match the PIC kit programmer pins as described in the PIC datasheet. The programmer that I use is the MPLAB PIC Kit 4. I wired the port pins to match the pin diagram for the 28-pin device. A reset button is necessary for changing modes without cycling power. R79 and C35 provide a slight amount of contact to bounce while remaining transparent to the PIC programmer. A set button is necessary to tell the board when to save the position of the pot while adjusting threshold levels. R78 is the pull-up resistor. I did not add a debounce capacitor because this would have interfered with the clock signal from the PIC programmer. According to the datasheet, pin 26 of the SOIC package can be set to be either digital RB5 or analog input ANB5. This is convenient for reading the value of the threshold potentiometer. RV1 is the threshold adjustment pot with a value of 10K. The purpose of R84 is to make the range of the pot match the range of the analog to digital converter in the PIC. The value of 1K on this schematic is not correct. It will be replaced by a 2.2K resistor. The green running LED will be a size 0805 surface mount LED from Light-On Optoelectronics. There are a few things to know before calculating the current limiting resistor R22. It is good to look at the maximum continuous current rating of the LED. From the datasheet, this is listed in large print as being 30 mA. But, if you look at the derating curve, you will notice that the LED would be much happier running at 15 mA. We need to know the voltage drop across that LED when it is running at 15 mA. This is a little less than 2 volts. It is also good to know how much current the PIC can sink. The maximum voltage when the output is driven low with a current of 51 mA is listed as 0.6 volts. The maximum current on the VS's pin is 250 mA. We have 9 LEDs that each draw 15 mA, so 150 mA total. The total power dissipation for the PIC is 800 mW, and the power used by the 9 outputs would be 0.6 times 0.015 times 9, or 81 mW. In other words, the PIC should be fine with driving all of the LEDs at once. We can now calculate the value of the current limiting resistor for the LEDs. The voltage will be 5 minus the voltage drop of the LED, minus the lowest output voltage of the PIC. The voltage drop across Q1 was not subtracted because the running LED does not have this. I actually chose a 180 ohm instead of 160 ohm because of price and availability. The program in the PIC will set port C to digital inputs and then turn off Q1 by putting a high on RB0. The LEDs will become back-to-back diodes and isolate the pins of port C from each other. This will allow the pins of port C to be pulled down to ground by the 8100K resistors, or pulled up by the 82.2K resistors, depending on the position of the dip switches. Either a relay or a small motor may be connected to the output. A 5-amp fuse is recommended to prevent damage in the case of a short. The purpose of R39 is to slow down the rise time of the gate of the FET. If the rise time on the gate is too fast, the FET will blow out. Q2 is the N-channel MOSFET. The FET was chosen for price and availability, rather than output current. Most N-channel FETs in the TO-252 package with the same pinout and a low threshold voltage will work fine here. D14 is the back, EMF, protection diode. This will protect the FET when the field collapses in the relay coil. D23 will speed up the turn-off time of the relay. This is counterintuitive and you may not believe that this actually works, so I will show you experimentally. This relay has a 12-volt coil, so J2 pins 1 and 2 are connected to the positive side of the relay. Most relays have no marking for positive, so it does not matter. Some relays have an internal diode and it does matter what coil pin is positive. When the relay turns off, the voltage spikes up until the transient voltage protection diode, D23, goes into breakdown. The relay requires 9 milliseconds to turn off. D23 has been shorted. The back EMF protection diode is still in circuit. The relay now requires 23 milliseconds to turn off. This demonstrates a savings of 14 milliseconds when D14 is present. Detection and alarms are indicated by both a beeper and a red LED. In some possible applications of this board, a beeper would not be desirable. R50 has been provided for the case where the user does not want the beep. The beeper, BZ1, requires 30 mA, so only an inexpensive transistor is required to drive both the beeper and the LED. The last part of the schematic design is the regulator that will change the 12-volt input voltage to the 5 volts that is used to power most things on the board. To prevent problems with inverse polarity, I added the diode D21. In order to reduce cost and board space, I chose to use a linear regulator instead of a switching regulator. C33, C34, C26 and C27 were recommended by the 7805 regulator datasheet, and I added a 0.1 microfarad bypass capacitor for every chip. The problem with linear regulators is that they convert the difference between the input power and the load power directly into heat. There are 10 LEDs on the board that would like to draw a total of 150 mA. I estimate that the regulator package and the copper area will probably be okay with dissipating around 1 watt. 1 watt is barely enough to handle the LEDs, but if the LEDs were to only draw this current for half of the time, the regulator would not overheat. This is why it is necessary to drive the 8 indicator LEDs with a pulse width modulated, or PWM, signal. The LEDs are the most power-hungry thing on the board, so if the regulator gets too warm, the PWM could be further reduced to less than 50% duty cycle. The LEDs are plenty bright enough even with this reduced amount of power. This is a detailed description of the firmware for the PIC microcontroller. There are many videos of how to install the MP Lab XIDE. So I will just begin with the PIC Kit 4 connected and this version 6.10 already open. Start a new project of type microchip embedded. This should be a standalone project. Select the PIC16F18455 device. Select the programming tool from the drop-down menu. Select the compiler toolchain. Name the project. Select the directory where the files will be stored. Click on the Finish button. Click on the blue-colored MCC button on the upper toolbar. This could require some time to load. Select MCC Classic. Click on the Finish button. Click on the Gene button near the project resources on the left side of the screen. This step is important to do after any changes are made to the configuration. This will cause the MCC to generate the code for the changes that you have made. Click on the blue MCC button on the top toolbar. Click on the Files tab just below the toolbar on the left side of the screen. The files under the In/B Project tab usually never need to be opened. The files under the MCC Generated Files tab can be really useful to open and view, but do not edit them except when necessary to fix a bug. If you edit one of these files and then use the MCC to generate a change, the Merge Files feature will come up. Click on the main.c file and the MCC generated template will come up. This is the file that will contain the program for the capacitive water detector board. A lot of the code that I write could be done another way. In the case of writing to port bits, the built-in syntax changed a few years ago and I wrote a function that was more resistant to future changes. Whenever I get a new chip or a new compiler, I always begin with a bit toggling program. This will make sure that the whole toolchain is working and also prove that the download function is working. You can also get an idea of whether the clock speed is correct. We need to open the MCC to set the port pin and the clock. The port pin for the test point in the running LED is port B pin 2. The Pin Manager window is at the bottom of the screen. Click on the blue lock icon that is in the General Purpose I/O output row and the port B pin 2 column. The clock setup is in the upper middle of the screen. We need the internal oscillator since this will be accurate enough for the water detect board. The clock frequency needs to be a little higher than the default in order to provide a faster response. A higher clock frequency will take more power, but this board will not be running on batteries. I will now try to compile and download for the first time. The error is due to a lack of any port E on this chip. This is one case where we will need to edit one of the MCC generated files. Click on the blue highlighted error message and the file with the error in it will open automatically. Comment out the line that has the error and close the file. Click Save the file when asked. The compile and download is now successful. The scope showed a solid 0. I had to go back and change bit 0 to bit 2, then I recompiled and downloaded again. It requires 129 microseconds to complete one loop. This is too slow, so I went back and noticed that the divider was set to 4 instead of 1. It requires 32.3 microseconds to complete one loop. This is now good enough to run the program for the board. I only use one interrupt in this program. This is for the software timers. The idea for the software timers is that you write a number to a timer and check back later to see if it has gone to 0. We need to tell the MCC to generate the code for timer 0. Select the timer 0 from the device menu at the middle left of the screen. I want the software timers to be updated every 10th of a millisecond, or every 100 microseconds. The range for the requested period will change as you change the settings for clock. The calculated actual period will not be updated until you click outside of the box. Click on the Enable Timer Interrupt box and then check the interrupt module to see if it is correct. We need to look for the function to set the interrupt routine. Look in the MCC generated files for timer0.c and double-click. The function that we need is towards the bottom. Click on the main.c tab just below the upper toolbar. I created an array for the timers and a define for the number of timers that are used. The comment for where each timer is used has proven to be really useful. This is the function from the timer0.c. This will set the timer0 interrupt so that my custom function will be called whenever there is a timer0 interrupt. The for loop statement will initialize the array of timers. Be sure to uncomment the 2 lines from the template. This is the code for the software timer interrupt handler. Each of the software timers will be decremented by 1 every 100 microseconds until they reach 0. I will add a heartbeat function that will test the software timers and will also provide an indicator to see if the code has hung somewhere. The heartbeat function is a state machine with 2 states. The first state will wait until the software timer reaches 0. Set the timer to the desired pulse width, turn on the LED, then go to the next state. This state machine can be used as a template for most of the other functions in this program. The main idea is to do something quick, decide to change state or not, then return control to the rest of the program. This method is especially useful for microcontroller firmware because there is no operating system to do the time slicing. I will set the pulse width to 100. This should result in a period of 20 milliseconds. The scope says that the period is 19.9 instead of 20 milliseconds, but this is close enough for this board. This modification to the heartbeat function is really old school. It is from the days when you wrote microcontroller code in assembly and a debugger was an expensive luxury. These days I use it just because I am too lazy to relearn how to use a debugger. I have not needed to use a debugger for a few years now. For debug mode, the initial state will be set to 2 and the heartbeat debug variable will be set to hex quadruple A, so that every other bit will be a 1. The heartbeat function will be called over and over again for as long as the power stays on. When the heartbeat function is called with the heartbeat state equal to 2, it will return until the software timer 0 becomes 0. The heartbeat pulse width variable will be reused here. This will be set to the heartbeat debug word only at the beginning of each serial sending of the complete word to the test point for viewing with the scope. This was done in case the heartbeat debug word were to change during the time when it was being sent and cause the output to be gibberish. Since this is the beginning of the word, the bit position will be initialized to 0. This state is now ready to change to the next state. The next time that the heartbeat function is called, the state variable will be equal to 3. So case 3 of the case statement will be executed. The first thing to do in this state is to check to see if all of the bits in the word have been sent. If all of the bits have been sent, timer 0 will be set to the interword time. This needs to be long enough for the scope to trigger only at the beginning of the next word. Since the word is done, the state needs to be reset to the beginning of the debug states. A1 is placed at the leftmost bit, or MSB, of the bit variable. This is so that the bits can be shifted out left to right and they will display properly on the scope. The 1 in the bit variable is now shifted to the right the correct number of times for the present bit. The output test point that is also the running LED will be set here. Software timer 0 is now set to the pulse width of a 1. The bit position variable is incremented and the state variable is incremented to the next state. If timer 0 is equal to 0 here, this is the end of the pulse for either A1 or A0. If this bit was a 1, this is where the output is set to 0. If this bit was a 0, this is redundant. In either case, it is now time to increment the state. If the timer 0 is not yet 0, but is less than the pulse width for a 0, the test point and running LED will be turned off so that this will be a short pulse. I added this because successive ones would look like a single long pulse. With this added, there is a gap from one to the next. This is the scope connected to the test point. The leftmost position is a long pulse that indicates a 1 in the MSB. I will now change the heartbeat debug variable to hex 5555. And then to hex FFFF. And, just for fun, to hex 3456. I will now set up the PWM for the LED and the PWM for the capacitor sensor plate drive. Both will use timer 2, so I will set this up first. PWM 6 will be for the LEDs. I will set the duty cycle to 50%. A function will be generated that will allow the duty cycle to be set by the main program, but I will not need to use it for this program. The output pin for PWM6 will be port B bit 0, or RB0. The duty cycle for PWM7 will also be 50%. The output of PWM7 will be set to RB1. Remember to click on the Gene button before closing the MCC. The generated code for the pin manager does not match. We edited the file to fix the problem with latch E, so the MCC will not overwrite the file. We still want the comment to remain, so we will leave it alone. The next difference is tris B. This change is necessary, so click on the arrow. To test the PWM for the LEDs, I will connect the scope to RB0, or pin 21 of the PIC. I set the period of timer 2 for 300 microseconds and the actual period is 298.4 microseconds, so this will be close enough. I set the duty cycle to 50% and this is correct. When you look at the LEDs, they will look dimmer than 100%, but you would not notice any flicker even if the period was as slow as 33 milliseconds, or 30 times per second. PWM7 should be the same because the settings were the same. 1 divided by the period of 300 microseconds gives 3.3 kHz, and this is the frequency that we used to test the capacitive water sensors. Next thing to do is to set up the push button switches. The reset is correct by default, so nothing will need to be changed. The set switch that is connected to RB6 will need to be an input. Digital pins should not have the register bits set to analog. All of port A and RB5 will be analog, but the rest of the port pins will be digital. In the MCC, click on the Pin Module tab below the upper toolbar. Click on the Registers tab below the Pin Module. Click on all the windows that need to be digital. To test the switch, we will need to look at port B bit 6. I asked ChatGPT to write a function to read a bit of port B and it wrote this. It works fine, so I have not modified it. I added this code to the main while loop so that the switch could be tested. The test of the set switch works fine. Next I will write the function to control the beep. The beeper is on RB3. I will change both RB3 and RB4 to general purpose outputs. First, I will add the define and the function definition. The beep function will need a variable from the mode switch. The variables need to be initialized. The function needs to be called from within the main while loop. I will change the debugging code so that the beep will sound if the set button is pressed. This is the beep function. It will look at the mode switch setting and invert the beep if necessary. Remember to remove the plug from the PIC programmer so that the set switch will work. The relay is connected to RB4. Add the function declaration and the defines. Initialize the port pin and the relay out variable. Call the function from the main while loop. Modify the debug code. This function will need a software timer, so the number of timers needs to be modified and a comment added. Relays are really slow to switch. The switching time can be 10 or 20 milliseconds. If a water sensor is right on the edge of switching and the turn-on point is too close to the turn-off point, the relay can switch on and off with a buzzing noise. This is really bad for the contacts of the relay and can cause the contacts to weld themselves together. The solution is to create a delay from the last change before the next change can occur. The variable relay out is compared to what it was at the last change. If it is different, the timer is reset to a value that will eliminate the buzzing noise and allow time for the contacts to cool down. The old relay value is then updated. If the requested relay state is the same as was the last time the function was called, the timer is checked to see if enough time has passed. If not, control is passed back to the rest of the program. Please ignore this redundant statement. Perfection can only be attained by those who don't do anything. Since the anti-chatter delay has been completed and the requested new state is stable, the dip switch mode setting is checked to see if the relay state should be inverted. The state of the relay is then updated. To add the mode switch function, I will first set up port C to output to the LEDs. The mode switch function will save these settings and then change them. The LED PWM will not need to be changed. I will call the read mode switch function after the system initialize function. The mode switches will only be read once, after a reset or power up. The values in these registers will need to be changed so that the dip switches can be read. These registers are explained in the datasheet. TRIS is short for tri-state or high impedance. This sets the port pin to input or output unless the ANSL register is set. If the ANSL or analog select register is set, the output driver is disabled. I will set the WPU, or weak pull-up, to all zeros for the port C inputs. The inputs may need some time to settle to the correct values because of the 100K pull-up resistors. This for loop will provide a bit of delay. Here is where I actually read the mode setting dip switches. I then restore all of the registers to their former values. I will now change the code so that the switches will be sent to the debug word. This will only happen on power up, so I will press the reset button when I want to look at a new setting. The switches that will invert the relay and beeper can now be tested. The LED function will need to use port C, so I will add a function to handle this. I will now add the function that will handle the LEDs. This function will monitor the values of the water wet array. For now, I will just set up the array and come back to it later. For testing, I will first set all of the array to 1s and then see if the LEDs come on. I will now set them to 0 and see if they turn off. Next is the function that will read the water sensor values in the threshold setting pot. I will add the analog to digital converter from the device resources. The clock settings need to conform to the TAD timing specifications. The ADC range will output a 12-bit word that ranges from the negative reference to the positive reference. I would like the positive reference to be a little less than the 5-volt supply to the PIC so that the voltage will be regulated and stable. A fixed voltage reference is provided and the choice that will give me the most range is the 4.096 volts. Port bits RA0 through RA7 and RB5 will be set to inputs for the ADC. I will check to make sure that these pins are set to analog in the pin module. Declare the function and the global variables. Initialize the arrays and variables. Call the function from the main while loop. Write the function just before the end of the program. In state 0, there are two things to set up. First is the channel number. The channel number will go from 0 to 8, but channel 8 is on a different port, so the channel is hex 0D. Second is the timeout. The timeout is to recover if the ADC fails to set the done bit. The MCC generated function that will start the ADC is called in state 1. State 2 will wait until the MCC generated conversion done function returns true, or until the timeout is passed. If the time limit has passed, the initialize function for the ADC will be called. The state will then be set to 0. If the ADC conversion is done before the timeout, the result will be saved and the state will be incremented. If the channel number is hex 0D, the value from the ADC will be added to what it was last time, then divided by 2, provided the result was not 0. It is not a good idea to divide by 0. This is an easy way to get a running average and to reduce glitches. If the channel number is 0 through 7, the running average will be stored into the water values array. This section is commented out because there are no threshold values yet. I will add a line to the main while loop that will set the debug word to the value that is read from the pot. Next, we need a place to save the thresholds. This needs to be in a memory that will still be there after power cycling. This is called non-volatile, or electrically erasable programmable read-only memory. The MCC will add the functions that are necessary to use this feature. I will create two arrays, one for the turn-on thresholds and one for the turn-off thresholds. The function that will initialize the arrays will only be called once when the reset is pressed, or when the power is cycled. The address for the non-volatile memory begins at hex 7000. The first 2 bytes will be used to see if the memory has been initialized. The only time that it will not have been initialized will be the first run after the program is downloaded. I will start with initializing the memory. There are 8 words in each threshold array. The array of 16-bit words that will be used in the program as the turn-on threshold will be initialized here. The word number needs to be multiplied by 2 to get the byte number. I used a left shift by 1 instead due to old habits. A logical OR with the base address and the byte number will give the complete address. The most significant byte is written. The address is incremented and then the least significant byte is written. The turn-off thresholds are stored here. Initialization is complete, so the key will be written here. For the case where the memory has been initiated, the 8-bit, most significant byte will be read, then left shifted and stored into the upper 8 bits of the turn-on threshold array. The address will be incremented and the byte stored into the lower 8 bits of the turn-on threshold array. The turn-off threshold array will be loaded here. I will now add a function that will allow the user to adjust the turn-on thresholds. This function will need to be called when the mode switch bit 3 is a 1 when the reset switch is pressed. I will adjust the heartbeat pulse width so that the green LED will blink slowly to let the user know that thresholds are now being adjusted. This function will not return to main. This is because the mode switch will need to be changed once the present threshold has been adjusted. The program must not act on the mode switch while it is being changed because indeterminate things could happen. The program will only read the mode switch after the reset switch is pressed or the power is cycled. These functions will need to be called each time around the loop. I will set the value of the present threshold to the position of the pot and also send it to the test point. The turn-off threshold will also need to be set. It should be less than the turn-on threshold. There is no hardware to bounce for the set switch. A short spike could be just a glitch and these should be ignored. If the switch is pressed and it was not pressed the last time, I will start a software timer. If the set button is released, or it is still bouncing, the saved state of the button will be 0. After one more check of the set switch, the variable that allows only one save per pressing of the set switch will be cleared. The beep will also be turned off. If the set switch has been on long enough for the timer to get to 0 and the threshold has not been saved for this press of the button, the beep will turn on to let the user know that the threshold has been saved. The address will be calculated based on the channel that is being adjusted, then the upper byte of the new threshold will be saved. The address will be incremented and then the lower byte of the new threshold will be saved. I will set this variable to a 1 so that the new threshold will only be saved once for each press of the set button. I found that it was a good idea to save the turn-off threshold also. I will now add the function that will adjust the turn-off threshold. The function that will adjust the turn-off threshold is nearly identical to the function for the turn-on function. The only difference is the array to be updated and the address to be saved. The commented out code that will update the water-wet array can now be restored. The code that will send the array to the LEDs has already been written and tested. I will set the dip switch to hex 8 to select the turn-on threshold adjust for channel 0. Press the reset switch so that the program will begin the turn-on threshold adjust function. Adjust the pot for around 2/3 underwater. Press the set switch so that the program will save the turn-on threshold. Set the dip switch to hex 10 to select the turn-off threshold adjust for channel 0. Press the reset switch so that the program will begin the turn-off threshold adjust function. Adjust the pot so that the LED will turn off at around 1/3 underwater. Press the set switch so that the program will save the turn-off threshold. It is now time to write the code to handle the modes. The first mode is hex 0. This is the logical and function. If all inputs are wet, the beeper will sound and the relay will turn on. Declare the function. Call the function from the main, while, loop. Add the function near the end of the file. If the mode is 0, all of the inputs will be ANDed together. If all of the inputs are 1, the beep and the relay will be turned on. Otherwise, the beep and the relay will be turned off. The next mode is hex 01. A logical, or, of the inputs will be done. If any of the inputs are wet, the beep and the relay will be turned on. Otherwise, the beep and the relay will be turned off. I made a breadboard with a switch to make it easier to test the modes. This is a test of the AND function. This is a test of the OR function. A mode for keeping a reservoir filled from a supply tank will now be written. Sensor 7 will be the tank empty sensor. Sensors 1 and 6 will be the empty and full sensors for the reservoir. Sensor 0 can be used for a flow sensor that will be checked to make sure that the pump is not broken. Sensors 2 through 5 will not affect the beeper or the relay, but they will still affect the LEDs. The fill reservoir function has 3 different modes. In mode 2, there is no checking of the flow sensor. This should be chosen if there is no flow sensor. In modes 3 and 4, if the flow sensor does not detect flow for a certain time period, this indicates a pump failure and the relay be shut off. In mode 3, the flow sensor can be off for up to 30 seconds before the relay will be turned off. For a delay of 90 seconds, mode 4 can be selected. The cases in the do modes function for the fill reservoir can be uncommented. State 0 of the fill reservoir state machine will set up for checking the time out of the flow sensor. If the time out is set to 0, no checking will be done. If the time out is not 0, the flow sensor will be checked. If the flow sensor detects flow, the timer will be reset. The state will then be incremented to 1. In state 1, if the pump is on and the flow sensor timer has timed out, the beep will be turned on and the relay will be turned off. This indicates a pump failure. The state will be set to a permanent error so that the relay will remain off until the power is cycled or the reset button is pressed. If the pump is not broken, the state will be set to 10. A number of non-implemented states were left here for later changes. In state 10, the supply tank will be checked. If the supply tank is empty, the beep will be turned on and the pump will be turned off. The state will not change until the supply tank is filled up. In state 11, the reservoir will be checked. If the reservoir is empty, the pump will be turned on and the timer will be reset. The state will then be reset to 0 so that the state machine can continue running. Modes 5 and 6 will control the pump for my hydroponic system. The pump will turn on when the power comes on. If the flow sensor goes dry, or if the reservoir becomes empty, or if there is a leak detected by sensors 1 through 6, the pump will turn off and the beeper will turn on. Declare the function. Initialize the state. Remove the comment from the function call. Insert the function near the end of the program. In state 0, the pump will be turned on and the beeper will be turned off. The pump timeout will also be reset. In state 1, the flow sensor will be checked. The timeout will be reset if the flow sensor is wet. If the time limit has been reached, the pump will be turned off and the beeper will be turned on. This is a fatal error, so the state will be set to a state with no exit. The reset switch or the power will need to be cycled before the pump can be turned on again. The reservoir will be checked in state 2. If the reservoir is dry, the pump will be turned off and the beeper will be turned on. When the reservoir has been filled and the pump is off, the state will be set to 0 so that everything can be reset. In state 3, water sensors 1 through 6 will be checked to see if there are any leaks. If a leak has been detected, the pump will be turned off and the beeper will be turned on. When the leak has been fixed and the pump has been turned off, the state will be set to 0 so that everything will be reset. State 4 will just set the state to 1 so that the state machine will continue running. Mode hex 20 will control a drip watering system. When the reservoir is not empty and any of the other sensors is dry, the pump will turn on. The beep will sound if the reservoir is empty. Declare the function. Initialize the state variable. Call the function from within the do modes function. Add the function near the end of the file. State 0 will check to see if the reservoir is empty. If the reservoir is empty, the pump will be turned off and the beep will be turned on. When the reservoir is filled, the beep will be turned off and the state will be incremented. State 1 will check all of the other sensors. If any of the sensors are dry, the pump will be turned on. Otherwise, the pump will be turned off. The state variable will be set to 0 so that the state machine will continue running. Modes 21 and 22 are nearly the same as mode 20. The difference is that sensor 1 will be used for a flow sensor to turn off the pump power as if is broken. Declare the function. Initialize the pump timeout, depending on the mode 21 or 22. Call the function from within the doModes function. Add the function near the end of the file. State 0 will check the reservoir. State 1 will turn on the pump if any of the plants are dry. State 1 will also set the timer for the pump timeout and set the pump on variable. State 2 will see if the pump is on without any flow detected. It will wait for the selected timeout period, and if there is still no flow, the pump will be turned off, the beeper will be turned on and the error state will be entered. All sensors are wet. I will change sensor 6 to dry and the pump will turn on. I will change the flow sensor to dry and start the timer. This is the error state for a broken pump. I will need to fix the pump and press the reset button. I will change sensor 6 back to wet and the pump will turn off. Sensor 5 is dry so the pump will turn on. The reservoir is now empty so the pump is off and the beeper is on. The reservoir has been filled, so the pump has turned on. Now that everything is running, it is a good time to find out how long it takes to go around one loop of the main while loop. The heartbeat can be set to normal mode and the pulse width set to 0. This will produce a square wave that changes state each time around the loop. It requires an average of around 600 microseconds to complete one loop. We can now set up a Watchdog timer so that if something goes really wrong, the hardware will cause the microcontroller to be reset. Open the MCC and click on the System Module tab just under the upper toolbar. Enable the Watchdog timer by selecting the second choice from the drop-down menu. Select the low-frequency internal oscillator as the clock source. Select the choice for window always open. Select 1 to 65,536 divider ratio to give a 2-second timeout. A 2-second timeout is desirable to prevent relay chatter in case of a really bad error. Remember to click on the Gene button before exiting the MCC. To test the Watchdog timer, I will make the debug word count up 10 times per second. If it continues counting up past the 2-second setting of the Watchdog, I will know that the Watchdog is not working. Choose a software timer. Timer 2 will not be used if the mode switch is set to 0. Change the heartbeat to debug mode. Initialize the debug variable. Add the new code to the main while loop. The Watchdog timer is now resetting the microcontroller every 2 seconds. Add the clear Watchdog macro function call to the main while loop. The debug word will now count up forever. Change the heartbeat back to normal. Remove the Watchdog test code. You can check how much of the data memory and the code memory that has been used in the lower left of the screen. There is plenty of room for your custom modes to be added. Revision 1 of the board was created in January of 2024. It is still running my hydroponic system today. Revision 2 was designed in February of 2024. This was the first revision that was completely built by PCB-Go. The improvements for this revision included a larger dip switch for more modes. Reset and set switches plus a pot were added for adjusting the thresholds. Revision 3 was not made. Revision 4 was designed in May of 2024. There were 2 improvements. The programming port, J1, was changed to a vertical socket with 0.1-inch spacing for ease of programming. The other change was that a socket and a jumper were added in case the user wants to replace the pot. The schematic and bill of materials will be on my webpage, www.rhwebco.com. I will also put the programming files there. I plan on putting the fully stuffed board and a bare board onto eBay, and I will try to keep the links updated. If they all get bought, the links may change when I restock, but you can always just search for 8-channel capacitive water detector board. Thank you for watching my video. Please like and subscribe.